In this quick video tutorial, I'm going to go over how to build and use a convolutional neural network, also known as a CNN, in Tensorflow and Keras to classify an image of an animal to output whether the image is a picture of a dog or a cat. A convolutional neural network is a deep learning model that will essentially extract details and patterns from an image and also the correlation between its features to be able to classify the image or different features of it. And we're going to do this in three parts. We're first going to load our images and labels to train our network. And then we're going to build the convolutional neural network and train it. And then finally, we're going to load a folder of test images of dogs and cats and use that data with a neural network to decide whether the image is a dog or a cat so we can test out our working model. Now, before writing any code, you're going to want to make sure that you have Tensorflow and Keras installed, or those packages installed. You're also going to want to make sure that we have Numpy, which is very important for handling arrays and just array computing in general. And then we're also going to want to make sure that you have the Pillow package for image handling and processing. If you have those packages installed and you have a Python environment that's set up similar to what I have here, then you'll be ready to go and we'll be able to jump into some code. So just check that out in the description below and make sure that you have all these requirements before you begin. Once you're ready to start coding, we're going to need some data to train our convolutional neural network on. We're going to need a lot of photos of cats and dogs to train our neural network. Now, instead of being the weird person that has to ask all their friends for pictures of their pets, what we're going to do instead is download a data set. And there's a really good data set at Kaggle.com, and I'll put this link in the description below. And they have a great data set of dogs versus cats, and it's 25,000 images of dogs and cats. So we're not going to train on all 25,000 of those images because it will take quite a bit of time. I'm going to simplify it a bit for this tutorial. I'm just going to use 129 images of cats and 129 images of dogs to train the network on. It won't be that great of a sample size to train a network on, but it'll be good enough for the purposes of this tutorial. So once you've downloaded that data set, or if you have your own data set, that's totally fine as well. But once you have that ready to go, you're going to want to set up your folder structure. So I've set up the folder structure in this way, and you can really change this around to how you see fit. But I have our file here that we're going to write our code in, imageclassify.py, our Python file. And then I have two folders, test folder and a train folder. Train folder is for the training data. So in there, I have cats and dogs. Cats folder contains 129 images of cats. I say 129 because it starts at 0. And then same thing for dogs. Also 129 images of dogs. So that's my training data. And then I have testing data, another folder where I just picked out a handful of images of dogs and cats. And this is what I'm going to use to test the neural network on to see its accuracy and see if it could recognize whether these images are cats or dogs. So that's kind of how I've set up the folder structure. You can change this however you see fit, but this is what I've done for this quick and simple tutorial. So once you've kind of set up your folder structure in a similar way, we'll begin typing in our code. But this is the next thing that you're going to have to make sure that you do. We have to make sure we have data to train the neural network, and we have to make sure we set it up in a way that's structured. So now to start jumping into the code, we're going to start in our file here, and I'm just going to start with the very basic things that we're going to have to add first. We have to import our libraries or modules, whatever you want to call them, so that we can access certain features and things from Keras and TensorFlow and so on. So I'm going to do from keras.models, we're going to import load model sequential, because we're going to be creating our own model, or just a simple model for making a convolutional neural network. So next I'll do that. It's convolutional 2D, max pooling 2D we're going to need, activation, dropout, flatten, dense, all those networks we're going to want. From TensorFlow Keras, we're also going to add some pre-processing, image data generator, and image to array. We can turn an image into an array of numbers. So all this stuff we'll just need, and we'll also import from our pillow library, things for manipulating our image, and from Numpy, we're just going to import that so we can easily deal with arrays, and then import OS so we could path files and load files from directories and things like that. So I think we have everything here that we'll need. Maybe I forgot something. We'll find out when we start running this code. But for now, I think that's all we'll need. And what we're going to first do is decide, okay, the images that we load in, what resolution are they going to be? You don't want to load in images that are really big. Like you might have pictures of cats and dogs at like 2K resolution, 4K resolution. We don't want to load that in because that will take up so much memory to load in and train that our graphic card probably won't be able to train on it, or our computer will run out of memory. It'll be really slow. We want to keep data to a smaller size so we could train these models efficiently and effectively. So I'm going to create two variables, image width and image height, and I'm going to define them as pretty low resolution, maybe 150 by 150 pixels. And that's what we're going to use to train our data on. It seems really small. It is really small, but it's enough. If you look at an image thumbnail, like if I go back here and I look at one of these images, I'm not viewing them in a really large size, but I still can tell what's a cat and what would be a dog. So it does have the data in that pixel resolution to be able to train the network. We don't need to make anything excessive. It'll just make it slow. So that's going to be fine. So I'm just going to put like a label here, and it'll just be our input resolution of training images. Whoops. I accidentally ran our Python control here. So there we go. Let's clear that. There we go. Okay. So we'll make sure we define our image size. Next thing we want to do when we load our images, and we haven't loaded our images yet, but this is something that I'm thinking of. When we do load our images, we want to pretty much take those pixels in the image, which are currently probably in a range from 0 to 255 for red, green, and blue. That's what makes up the colors that we see on our screen to some extent. Instead of that, I want to take those pixel values and just clamp them down to 0 to 1, or normalize that data. I don't want them to be pixel ranges from 0 to 255. I just want to normalize that data from 0 to 1 to handle it a lot easier. So to do that, we can easily normalize, or maybe I'll say rescale pixel values of training images from 0 to 255 to 0 to 1. So to do this, I'm going to do a new variable, train rescale, and I'll make it equal image data generator. Rescale it to a range of 0 to 1. So we'll do that. And once we've done that, we have to load our images. So I'm going to load the images next. And to load our images, we already have them in a folder structure. I'm just going to go back here to look at this. We have training folder, and then we have cats and dogs. We have them grouped by folder. And the great thing about that, having them grouped by folder, is you can use that for labeling. Instead of having another file that says this image is a cat, this image is a dog, if they're in folders that are labeled cats and dogs, we can use those folder names to automatically add labels to our images. And to do that, we can use something called flow from directory. So what we can do is we can say our training data will equal, and then I'll do this, or train rescale, our normalized images. And then we'll do flow from directory. And what this will do is it will load images and labels based on the folder names. So I'll add a comment in here, flow from directory will load images and label them based on folder. There we go. And how do we use this? Well, we specify the folder. So in this case, it's going to be train slash, and then target size. We already know what we want our size to be. It's going to be our image width and image height, which are those variables we defined that are 150 by 150 pixels. And then batch size, we'll do 32. And then class mode will be binary. It's either one or the other. And that is it. So that's going to be our training data, loading on all those files, specifying the height, batch size, and what kind of mode. Now, before we go too much further, there's a few things I just want to go over. So why are we using image data generator instead of just doing our rescale and that's it, and just loading our images? The image data generator is pretty much a way of loading a bunch of images, and it's going to do things like flip them around, rotate, scale them, to kind of help the training process. And it's going to do this in real time or kind of on the fly, and it will often give us a much better performing model. And then in our flow from directory, I put our batch size to 22. That means it's going to load images in, or 32. It's going to load our images in at 32 images at a time and process them and then load 32 more. And this is a way that you can kind of make sure your model performs quickly. You can make that batch size smaller. It might update weights sooner and quicker then, but I feel like this will be an okay value to start with, but it's just another way of being able to modify kind of how you're training your model, how many images are you loading at once, and that can definitely have some impact on your result of your model. So they are things that you can kind of play around with. But in this case, it should be fine. But I just want to go over that so that we exactly know, what the point of this is and why am I setting the batch size to 32. I think 32 images at 150 pixels each is going to be totally fine. And it'll be a good number to use. So sometimes it's just guessing. Other times you might have to play around with it and compare your model and see if it performs better or worse. So now we're going to actually build our model and its layers. So we're going to define our model and its layers. So model equals sequential. And then we're going to add a layer to the model. So model.add convolutional 2D network. It's going to have 32 filters with a kernel size of 3 by 3 pixels. Its input shape or size is going to be our 150 pixel image width and height. And then number of channels, 3 channels for our image, 3 channels for red, green, and blue. Now, even though I set up here that we are normalizing our data, we're normalizing each one of those channels. We're taking the red channel, the green channel, and the blue channel, and we're normalizing the pixel values to 0 to 1. Not 0 to 255. So even though that's happening, we still have 3 channels. We have a channel for red, green, and blue. So we still have to make sure that we define our amount of channels here. So 3 channels in our image, red, green, and blue. So that's our first layer. And maybe I'll add a comment in here that says, okay, first layer is a convolutional 2D network, 32 filters, 3 by 3 pixel size. So I can just define that here. And it'll capture low-level features, things like edges, curves, so on. Okay, then our next layer that we're going to add, another layer, is going to be an activation layer with a type ReLU or ReLU. And what this is, so this is an activation function that's going to replace negative values with 0. So anything that turns negative or not positive is just going to end up filling it with 0. And then on top of that, we're going to add another layer called max pooling 2D. We'll define a pool size, which will be 2 by 2. And this, I'll add a comment for that as well. So the max pooling 2D is pretty much there to reduce the image. So it's going to take the image and it's going to take maximum values from a 2 pixel by 2 pixel region and store that. So it's a way of just pretty much shrinking the image down and simplifying those features even further. So the whole point is that our neural network is going to look at our images scaled down, different features of it, edges, curves, shapes. We need to train it to start to recognize patterns and textures within that image. And to do that, we want to squish the image down and do things to it to make those different patterns and features recognizable. So that's going to be kind of what our max pooling 2D layer is going to do. It's going to reduce our image by taking max values from that 2 by 2 region. So that's going to be kind of the first section to our model. Now for the next section, nothing really special. We're just going to repeat that again. So model.add, we're going to do again another convolutional 2D network, 32 filters, 3 by 3 pixel size. That's it. Okay. And then same thing, model add, activation network, or not activation network, activation function with the same, exactly the same type. And then finally, max pooling again, reduce the image. That's it. We're just copy and pasting. We really could just copy and paste. And then we'll add another section. So this one is going to have a bit different of a goal. We're going to extract more features, but this time use a 64 filters at 3 by 3 pixels. So we'll do model add convolutional 2D network, 64 filters, 3 by 3, and then same thing. Max pooling, activation layer, or activation function for that layer, and that's it. So we're just doing a little bit different. Now, what we're going to do is take the results of all this and we're going to flatten it. So the next thing we're going to do is flatten our output into a one-dimensional vector. So we're going to do model, add, flatten. And it's going to flatten it into a one-dimensional vector. So not two-dimensional vector, just like a line of vectors, and that's it. And then finally, we're going to pass that one-dimensional vector into a dense layer. So we're going to make a new layer that contains 64 neurons. That's a dense layer. So we'll pass these one-dimensional vectors to a dense layer with 64 neurons. And then exactly the same thing. We're going to add our activation function. So copy and paste that. And then there's one more thing we're going to do a little bit unique right here. We're going to add a dropout of 0.5. So what does this dropout do? So we're going to first do that activation layer, or activation function, which returns pretty much only positive values. Anything else will become, anything that's negative will become 0 with that activation function of RELU. And then our dropout layer. So why are we adding the dropout layer? It's going to have, you see here, 0.5, which pretty much means 50% drop rate. And that's going to prevent overfitting or overtraining of the data. It's going to drop like 50% of the values or of its complexity. So we're going to do this to prevent it's really just to prevent overfitting or overtraining with too much info. So we're just going to say to prevent overfitting, and I guess you could also say, it's going to reduce complexity, but really that's the whole purpose of it. So we'll do that. And then we're almost done. But after doing this, we're going to bring down its simplicity a bit more. What we're going to do now is create one more layer. So model add. We're going to make a dense layer now with one neuron. That's it, just one. And this is going to be a dense layer with one neuron. And on top of that, we'll do a activation function. We'll then pass it to an activation function, that one neuron, called sigmoid. And what sigmoid is going to do is pretty much produce a probability value. So it'll produce a value between 0 and 1 that represents a probability. Okay, so we're going to say here we had our dense layer, one neuron, and then we also do a sigmoid activation function to produce probability value. That's really it. And then finally, we'll compile the model. So we'll compile the model. So we'll do model.compile. And loss will be binary cross entropy. This is good for cross entropy. This will be good for really classification. But again, you can always play around with these. There might be better performance in other methods. And then we'll use our optimizer. We're going to use our MS prop. So this usually works good for image classifiers, but again, you can try with different types. And then metrics are just going to be accuracy. And that's all we need to compile our model. So we pretty much just run our image through all these different things. Convolutional 2D network, 32 filters, 3x3 pixel size. We reduce it, repeat it. We do this over and over again, but in the end, we get it down to be one neuron that produces a sigmoid probability value. You use a sigmoid activation function to produce a probability value in the end. So even though we're taking an image, we're training it, the result that we want is a 0 to 1, whether it's a cat or a dog. So that's kind of what we reduce it to in the very end. So once we've done that, it'll compile our model, then we can train our model. So I'm just going to finish this comment here. And again, it's probably good to test different types of loss and optimizers and things, and just get a feel for what works the best for different tasks. Generally, you can look online and find out what is often used and what performs fairly well, but sometimes you'll be surprised and you might find out combinations that work better than you expect. So I'll just use this as a recommendation. You can give this a try, but feel free to experiment. And now what we want to do is train our model. So we're going to do train the model, and this is going to be really easy. Model.fit generator. And we'll take our training data, steps per epoch, we'll do 8. And then how many epochs do we want to train for? We'll do 128. I think that's good enough as a test. Probably should do way more to get good accuracy, but this will be quick. Now, what is steps per epoch? Well, steps per epoch is pretty much going to be, and I think I did this wrong, it's not it's steps per epoch. Steps per epoch is going to be how many times the weights are updated per epoch. So every time it trains, every time it trains the images, which is considered an epoch. The steps per epoch is how many times are the weights or the connections between these neural networks or the neurons updated. How many times? So we're updating it 8 times per epoch. And that might give you better data and better results. You don't want to do too many steps. Sometimes that might cause problems, but it's a way of updating the model weights within a training epoch, within a step of going through and training that data. So often updating those weights more often may give you better results. And again, there's no ideal number for these things. You have to test and find out what works best, what gives the most accuracy in less amount of time. It's something that you really have to experiment with. And what I'm putting in here is just something that I've blocked in that seems to work okay, but ideally it's not a perfect setting. It never will be. It's going to be different depending on your data set. But that's what steps per epoch does. How many times it updates the weights or connections between these kind of like neurons. And that's pretty much what it's doing. So after we train the model, we'll save it. So save the model. So we'll do model.save weights. Save it as like, I don't know, model weights. And then also save the overall model that we can use. So model, let's call it Keras. There we go. Now what we want to do that we've trained the model on our data set and we've saved it, we're going to now get a list of our test images. So, we'll get a list of all images in our test directory. So let's just go back to our folder structure here for a second. So I'm going to open up the folder structure. So in our folder structure, we got our test images. So we need to get all these images in a list. So to do that, I'm going to pretty much go here. I'll define a variable called test images. It'll be our list directory of that folder test. And then we're going to loop through those images and run them through our neural network or our convolutional neural network. So to loop through our test images, we will just go for image in test images, a list of images in our test folder. We'll take our image. Take our image, we'll open it. So we'll do image.open. And in our test folder, we'll open the image name. We'll then resize the image, resize it to our desired image width and height, which is 150 pixels by 150 pixels. And then what we'll do is turn that image to an array. And then finally, what we'll do is we'll add a dimension to that image. In this case, axis 0, which is just to the left side of it. So we'll just add an axis to that image array or that array of numbers so that we can just pretty much run it through our neural network properly, just preparing it for running it through our model. So finally, we'll use our model to produce our probability of whether the image is a cat or a dog. And to run the model on these images, really easy. We'll just do a result variable and we'll do model.predict and use our image. And we're just going to loop through those images, predict it. Once we get that value, that probability value, that will determine if it's a cat or a dog. based on probability prediction, we'll pretty much just end up with if the result that we get, and here we go, we'll do if that result is bigger or equal to 0.5, it's most likely a dog. Otherwise, there's only two ways it could be. It could either be a dog or a cat. So if it's not more than 50% sure that it's a dog, then it has to be a cat. So that's going to be our code for determining whether that probability value is a dog or a cat. And then we're going to output the results. So we'll do output the prediction or classification. So we'll print some text that says the image, and then that image will be the image that we're loading or on. And then we'll say is a, and then we output our prediction here, dog or cat. So that's all the code. So we load our data, we define our model and its layers, we compile the model, we train it, and save it, and then we load in our test data, and we use that model to predict. So this is all our code, and I'm going to save this, and we'll give it a try and see if there's any errors. There might be, but we'll find out. So before we run this, I'm just going to make sure we have all of our data. So we have like our training folder, cats images, dogs images, make sure all the naming's correct, the folder names match what they should match. If I look here, I have like train, what is it here? Train, okay, should all be good. So let's give this a try. I'm going to go here and go into the proper folder. So I'm just going to go into our folder here, which is image classify, and then run our Python file. Let's see what happens. Any errors, any problems? Okay, found 258 images to 2 classes. Here it goes. Starts training. So here's training the epochs. It's done 18, 19, 20 out of 128. So we have to wait a little while. Now you can see the loss function's pretty low, 0.0 something. That's great. But every now and then you might see it go to a larger value. Like I've seen it go a few times here to positive values or values greater than 1. That pretty much means there's a little bit of a problem with that training of that image. That's normal to see as long as it's not happening a ton, or as long as training isn't overall getting worse and worse. If it does, you might have to modify your model or your data. Now I do get an error here. I typed something probably wrong. What is it? Expand dim. What did I do wrong? So line 78. Yeah, so I did a little bit of a silly thing here. Not expand dim, expand dims, expand dimensions. So I'm going to have to rerun this. That's okay. But we'll see this again. Found 258 images, 2 classes, the dogs and cats folder. And again, loss amount. See, it starts fairly high, 0.2, 0.5. But over time, you can start seeing it's getting lower. So that's good. That's a good sign. You want to see that amount reduce. If that amount starts going to 1 and above 1 all the time, then there's a problem. So it gets hard sometimes training, because you could train a model and it can get really good, but then you can continue training it and then start to see a decline in its results. And that's common. That can happen. And that's the tough thing about training any sort of neural network. There's a point where it starts declining or not getting any better. But let's see what happens here. So it trained. It's, at the end here, the loss didn't seem too great. 5, 5, 3, and 2. Not the best. But let's see its outputs here. So it says test 001 is a dog. Let's go find out if that's true. So I'm going to open up the folder here, test So test 001, it's a dog. Test 002, it's a dog. Test 003, it's a cat. Test 004, it's a cat. Test 005 is a cat. Test 006 is a dog. So I was right. It had 100% accuracy with this small test set of, a few images here, 6 images. Now, this is a little bit not the best because these images here are taken from this data set. So it probably worked out pretty well. Like if we look here, cats, dogs, some of these cat images, like that cat image there, is one of the same ones here that I used to test. So that's not ideal because some of this data is the data that it trained on. To really see if it's classifying these animals correctly, I should be taking images that weren't included in our training set. And that's going to give me a much better result of, is this model actually working how it should? So that's something to keep in mind. You don't want to test the network on the images or on the exact same images you use to train it on, because there's a little bit of a bias there. You want to use images that it didn't train on to see if it could predict what those are. Hopefully this video helped you grasp the idea of how to create a simple image classifier using convolutional neural networks. If you did find this video useful, please like and subscribe. And if you're wanting to learn more about this stuff or you're enjoying this type of approach, please let me know in the comments below of what you'd like to see next. And don't forget, if you're part of the Patreon, you will get access to this PDF, which covers the code and the overview and explanation of what we've done in this video. And if you aren't part of the Patreon, you can check out a link to that in the description below.